Hello everyone. In this video, we discuss explainable AI, known as XAI, and a well-known method called SHAP. In machine learning, and in particular in supervised learning, we focus a lot on making predictions. However, in many domains, such as medicine, finance, autonomous driving, understanding why a model makes a specific prediction is very important. And one way to do this is a method called SHAP, Shapley Additive Explanations, which is based on cooperative game theory and allows us to understand the contribution of each feature to the model prediction or the model output. So in this case, you can think of this prediction task as the game, and we want to understand this for a single instance of a dataset. So meaning one of the samples that we have in our dataset. The players here are the feature values of that sample or instance. And what we are really looking for here is the gain. And the gain here is defined as the difference between the actual prediction of our model and the expected or average prediction. Why do we care about the expected or average prediction? Because we really want to know the baseline here, meaning that if no features were known, what would we get? And now that we know these features or how these players are basically acting here, how do they contribute to the difference between the actual prediction and the expected or average prediction? And therefore, the goal of SHAP is to ensure a fair distribution of this difference or this gain among features. And SHAP allows us to answer questions such as how much did each feature contribute to the prediction? Here we have the link to the original SHAP paper. So you can see that this is available on arXiv. It's a very nice paper to read that was published first in 2017. And also SHAP comes with a very nice library. So this is a library very similar to NumPy, SciPy, Scikit-learn that you can use to be able to get what we call it as SHAP values. And here you can see a very quick sort of like a snapshot of this, that we have a model, we have a couple of features, and the way that we explain this is by understanding the contribution of each feature. So features can add to the gain or can reduce the gain. And that's here you can see that it's been color coded. So to explain this more, now let's go understand a little bit the basics and mathematical explanation of SHAP. SHAP decomposes a model's prediction by attributing the difference from the expected value or average value to individual features. So this E of f of x here is the average or expected output value. This f of x is the output for the instance x or input x. And we write this as this additive explanation, where this phi1, phi2 to phi p, each one explains the contribution of the corresponding feature, meaning phi1 is the contribution for feature 1, phi2 is the contribution for feature 2, and we assume that we have a total of p features. And as we mentioned before, something that is very important to remember is that these sort of like contributions, these phi's, can be positive or negative. So positive means that that feature increases the prediction relative to the baseline, and this is our baseline. And negative means that the feature reduces the prediction relative to the baseline. So this is the idea of the gain in this cooperative game theory that we just mentioned. So what is this E of f of x? So this is the expected value of the model's prediction over the entire data set, or data set that we provide usually as training. So we have to always have a subset of data for explainability, and that's sort of like the average of the model predictions over that set. And the way you can think about this is that it represents the average model output if no feature values were known. So this is our baseline. And you can write this as 1 over n summation over n of f of xi's, right? So if you have n samples in the whole entire data set or portion of your data set, you're going to add all of them together, divide by n, that's your average or baseline. So we can actually show that how we can in general find these VIs, these contributions of each feature I. And the way that works is very simple. So we have this set of all features f, and then we're going to subtract the feature I. So this is what we use in set theory for subtracting. This means that we're going to subtract that feature I. And then we're going to consider all possible coalitions or subsets that we have here, meaning that they do not include I, but all other possible combinations of features. And for each case, if we come to this part of this equation we have, we're going to find the contribution of these features in the set S. And when we add the feature I. So this will give you that gain that we discussed before. And the nice thing here is that you're considering all possible combinations of the cases where we have I and we don't. Very similar to, for example, when we have the binomial random variable and you look at the probability mass function in probability, we need to find the right coefficient here. So this is just sort of like a constant to make sure that this gives us that additive explanation. So here we're not going into too much sort of like details here or too many details, but this is sort of like a term that we need to make sure that when we find all these contributions, this is properly adjusted based on the size of this S and F, right? Because S can have different sizes. It's a subset of all features excluded I. And in general, as you can see, if we have a lot of features, this can be a very difficult quantity to compute. That's why this library that you see here has a lot of different ways of approximating that formula that we had. But overall, the goal here is to understand how this works and be able to interpret our result. So in the case of linear regression or in general regression models, what we have is very straightforward because we can understand the gain or the difference between a real valued number and the expected outcome. However, this can be a little bit more complicated for classification models because we are, for example, in logistic regression, we are working with probabilities that each point belongs to one of the classes. And that's why we mentioned the idea of log odds space. So in fact, in the case of classification models, what we do as to be considered as the output of the model is this log odds space. And this is exactly what we have before the sigmoid or softmax function, which by definition is this log of probability of y equals 1 over probability of y equals 0. And this gives us that linear combination or weighted combination of the input features. So these xj's are the feature j, and then when we solve a logistic regression model, we find these coefficients beta j for each xj. And for now, I mean, we kind of like ignore this beta 0 because we want to look at the contributions of each feature. So that's why we mainly focus on this beta j. So something I'm going to do in this experiment that we're going to focus on next is that I will find SHAP values, and then I'm going to just look at the individual feature contributions just by looking at beta j, and to see that these things are very different, right? Because the way that this works, this equation, we are looking at the individual contribution of each feature. And if we have correlated or dependent features, we know that this is a problem because then logistic regression may distribute these beta j's in different ways to these features. However, SHAP, if we look at it, is using a way more advanced method to find the contribution of each feature. So that's something very interesting we're going to do. But for now, this was I wanted to provide this information to understand why we mean by outputs in classification models. We mean the log odds space. And beta j's are the coefficients, xj's are feature values. And if we want to convert this really to a probability score, we can do that because we know that from the discussion that we have, probability that y equals 1 in the binary logistic regression, it's simply 1 over 1 plus e to the negative log odds of x. So now let's look at an experiment here. So we import NumPy as NP, Pandas as PD, and in this case we work with a data set called breast cancer data set, which is already included in scikit-learn's datasets module. And in this case we're going to load this data set. So if we look at the data part of this object here, we get our input features. We also have our targets. I can show you what's inside here. So if you look at this data metrics or feature metrics X, you can see that if you're looking at the first 5 rows, so that's the first 5 rows, we have 30 features here, right? Information such as mean radius, texture, parameter, area, etc. So for each instance here in our data set, we have 30 features, and these are the names that we have. So what we really want to understand here is that what really makes us to understand the behavior of our model in that log odds space. And that's important because then the log odds can be directly translated to a probability score. So as always, we're going to divide the data into 2 sets, training and testing, with 30% for testing set. And we are going to use logistic regression model here for our classifier. One thing I want to mention is that the library, especially that we have for SHAP, works with almost all classifiers and regression models in scikit-learn. So you are not just constrained to this, but this is something that we have already covered. So we're going to instantiate this classifier, and then we're going to do model fitting. So this CLF now is a fitted classifier, and now we're going to make predictions on the test data. So here we're going to look at the confusion matrix, which shows that this is a good classifier. So that's the typical supervised learning scenario. We train and then we evaluate. However, right now, we do not know why we make predictions in a way that we have right now. Like what exactly is driving these predictions? So that's what we want to do. So in order to do that, after installing SHAP, and if you want to know exactly how to install it, please check out the documentation page of this library. We're going to use SHAP.explainer. So that's the most important or core function in SHAP that allows us to find these contributions. And what it really does, I would say the most important task is that you need to have this CLF, this classifier, which is like the function f, and the training data that we have. So one of the things that this function does is to find this baseline or the average output over all the instances in that X train. And based on this, now when we go to the testing stage, we can measure the contribution of each feature for all instances of the test data set. So in order to use this, we use SHAP.explainer. We provide the classifier, training data, and once we instantiate this and we define this explainer, now we can say explain X test. And this gives us those SHAP values. So it means that for each instance, I should have 30 values because we have phi1, phi2 to phi and those are the values that we have stored. And obviously, larger values and absolute values are better because it means that we have higher impact on the model output in the log odds space. So we run this. So you see that in this case, this is pretty fast since it's a simple model. And so we store the result in SHAP underscore values. If we just look at the shape of these SHAP values, you see 171, which is the number of testing data points, by 30. And 30, we know that's the number of features. So it's P here equals 30. And if you want to just look at, like, let's say the values of these 30 elements for the first testing data point, So you can see that these are the SHAP values that we have. And you can see that some of them are order of 10 to the negative 1 and some 10 to the negative 5. So you see like the differences in the range of values that we get. And you can look at this for any other row of these SHAP values array. So like row 2, which is index 1, or 10, 100. So you can see all these numbers here that you want for these SHAP values. So we can look at these individually, but that's not very helpful. So the nice thing we can do is to aggregate these results and plot nice figures. So one of these is this summary plot, which is a summary plot. We provide SHAP values, X test to know exactly the names of these features automatically. And then we can say that, okay, here we want to have a bar plot. On the x-axis, we have the mean or average of the absolute SHAP values. And we have to do this because remember, SHAP values can be positive and negative. A large negative number still can mean that it can have a lot of impact our model. So that's why we take the absolute value. So we have now just non-negative values, and then we take the average. And this is kind of like can be viewed as the average impact on model output. And according to this mean area, so this is one of the features that we have, one of those 30 features, as the highest impact on our output in the log odds space. Then the mean parameter, worst area, area error, etc. So the nice thing about here, so there are a couple of observations. So first, if we have access to domain experts, we can ask them whether they really think like mean area is one of the most important features or not. That's a question that is probably can be very interesting discussion with domain experts, is depending on the application. And the other thing, it seems that according to what we see here, although we have 30 features, it seems that 10 or so features are enough to explain the behavior of this model. So this is very helpful because in machine learning, we usually work with high dimensional feature spaces. And it is important to be able to focus only on a couple of features that are very important to explain the behavior of our model and answer questions. Why did we get this prediction? And you see that some of these are basically they do not have any impact on our model. So something that is very interesting here that we can do is that since we have trained this classifier CLF, we can look at those coefficients, those beta j's that I mentioned. So what logistic regression does, it multiplies each feature value by coefficient. And also very similar to what SHAP does, I can find the absolute values and then I can sort them and change the ordering to make sure when I plot them, I get a very similar plot where I get coefficients from the largest absolute value to the smallest. And this is what we get here, which is very interesting in a sense that you can see this worst concavity, for example, is like probably, yes, like one of the least important features that we have according to SHAP. And then mean area, which is the most important feature in terms of model impact from the SHAP analysis, is actually, let's see if we can find it. Yeah, it's like almost at the end of this list here, right? So I do believe this is not even among the top 20 features that we have according just to these coefficients of logistic regression. So all in all, what we're trying to say here is that we can always, with simple models such as linear or logistic regression, look at the coefficient values. However, that may not be necessarily very helpful. And one reason for that is that in many cases, a lot of features are dependent or correlated in some ways. And these coefficients that we find from logistic or linear regression can be indeed very misleading, because when they distribute these contributions to these features, we do not necessarily have a very unique solution and they can be divided in multiple ways. However, SHAP tries to really do a fair assignment of this impact to features because it's using a way more complex way of finding feature importances. So it's considering all possible combinations of features that they do not include I, and then they include I separately and measure the difference. And so in this case, although this is a lot more computationally expensive, can be a lot more informative to make sure that we have a fair way of measuring the importance of features. So overall, SHAP is a very nice method for explainable AI. It has a very nice library that you can use. As you can see here, very nice documentation, how to install it. So for example, I talk about installing SHAP. You can use this using pip method or conda install. So you should be able to do either of these methods. And also has this library has a lot of explanations about how to use SHAP with linear models, neural networks, even for more complex cases where you want to do like text generation and understanding the contribution of each features, image classification. So very, very nice library. I hope you found this video helpful.